elements of a space when you talk of it. Really, space here means about 100 kilometers, up to 100 kilometers, you can assume that this is atmosphere. That atmosphere, of course, thins very much by the time we go to 100 kilometers, even thinning further. But above 100 kilometers, you call it a space. And this space has got high vacuum because of the fact that the atmosphere is very rare there, very rarefied. Then you have got a lot of radiation that comes from the outer space, like the charged particles, electrons, protons. The solar radiation comes in. Then there are other types of radiation like ultraviolet and those kind of a thing. So there are very lethal radiation that pervade the space. The third thing is the space is extraordinarily cold. Actually, the temperature of the space is what you call as 2.7 degrees Kelvin. It's really the coldest that one can experience. So if you look at all these kind of a thing, you are really talking of a very hostile environment. And if you want to put an object, a man-made object into that thing, you need to have a high degree of ability for it to function under this hostile environment with reliability, with confidence that it can function. So these are the challenges of a technology that we need to do. So you need to build satellites which can be then used by orbiting it around the Earth. What happens when you try to acquire space? What it means by acquiring space or try to get vantage point of space, putting an object there, means you have to escape from the gravity of the Earth, but still use the gravity of Earth to go around. It's almost like what you call the centripetal force, centrifugal force. Many of you youngsters would have learned in your classes. So this is a balance between the centripetal and centrifugal forces. If you take a stone and then put it on a string and then move it, you can feel that force on your hand. It's exactly what happens when the satellite moves around the Earth. And so these kind of satellites then becomes a very useful tool to look at the Earth, look away from the Earth, and that becomes a very potential means of doing quite a lot of things, some of which we will see now. But then building a satellite is a lot of engineering, and this university of course has very good important courses on engineering, and so I may say that this is an interdisciplinary product, a satellite. It has structural engineering, thermal engineering, communication engineering, digital electronics, electro-optical system, electromagnetics, and control and guidance, and so on and so forth. So there are a number of engineering disciplines that have to come together, and they have to be put together in the form of a functioning system, a product, and that which you call a satellite. So in order to understand this kind of a thing, you need to have teams which work in several areas, but they are able to bring together all their expertise to make sure that you have an ultimate product, which is the product of all these engineering disciplines working together and interrelating to each other. So that's what we wanted to initially must, and then it has to go and function in the hostile environment of space. That is where the Aryabhatta idea was born. The first of the satellite we wanted to build was even smaller than that. About a 40 kilometer, what we called as Rohini, was the one that we wanted to build to get master this various art of building a satellite. But in the meanwhile, those were the years when India was very close to the then Soviet Union. And the Soviet Union wanted to help India in the space program in those years. What I mean is something like 60s. So the ambassador of the Soviet Union called Dr. Vikram Sarabhai, and he asked him, why don't we work together in building the India's first satellite? And then Sarabhai said, yes, we could do that. And then Sarabhai explained outside, no, it should be much bigger than that. He asked Dr. Vikram Sarabhai, what is the weight of the first Chinese satellite, he asked. And Dr. Sarabhai said, it's about 160 kilograms or so. At least make sure that the first Indian satellite is heavier than that. So that is a criterion that the ambassador said, and we will build that. So that was the genesis of Aryabhatta. The Aryabhatta was to learn the method of building a satellite, a multidisciplinary product to work in the environments of the hostile space. And then there was this collaboration with the Chinese. By the time Soviets had already done quite a number of satellites, so they knew precisely the art of making this. We jointly built together. But it's also what is interesting is that we wanted to also not just try only prove the technology alone. Use this opportunity to go and outer the space and try to do some scientific experiments. So we put also 3 scientific experiments into it, to look at the sun, to look at the radiations coming from outside, and also to look at the satellite environment, because even at those altitudes of 300, 400 kilometers, there is a residual atmosphere, but what you call as an ionized atmosphere. So you can look at all those kind of a thing. So that was the objective that was put as scientific, but more important is to study the method of making this particular satellite. What I would like to convey is this was a very tall order to do it in 30 months, because that is all the government gave. At that time, Madam Indira Gandhi was the Prime Minister, and he said we need to do it in the next 2.5 years. We didn't have the right number of people, we didn't have the experience of building this, we had to create infrastructure. So this entire gamut of things was done over the matter of 30 months, and by 36 months, that is within 3 years, from the point of conception to the delivery and launching, we achieved it in the 36 months. It's considered as a kind of a record for a kind of background in which we are. We don't have that kind of an industrial support for this, the design support, the expertise and the infrastructure. But in spite of all these hurdles, we could put together a team of youngsters, many of you are your age here, and that they could build this satellite itself was the most creditable experience that we had. And that was the first story, that of Aryabhat. And then we having built the satellite, then we wanted to know now what will be used for. Sarabhai has envisaged that it will be used for education, it could be used for communication, it could be looking at natural resources survey. So first thing we decided is that we will try to adopt this satellite. We were working with the Russians, and the Russians always take care by saying that you should build a standby model, and in case the first thing happens, something goes wrong with the first, then you should go to the next one. So we had a standby model. So we built a standby model, but we thought that how do we use it? The whole interest then was how to look at the natural resources of the earth. What you try to do is you put a camera in the satellite, take a picture from that altitude of 500 or 600 kilometers. You can have a very perspective view, because I stand on a higher level here, I can see the whole hall. If I come down, I can see only limited hall. So the whole idea is to get a perspective view of the ground by taking a camera picture from the space. So that is what we wanted to do. That is called as a remote sensing satellite. It's a very rudimentary system we thought of, with 1 kilometer kind of a resolution, which can see broad features like river systems, geological features, large forest trees or delta systems of rivers and so on. But you not go into the nitty-gritty details of buildings or those kind of a thing. But we thought that we should get our hands. And that was the genesis of Bhaskara. I have only one interesting episode about Bhaskara that I would like to convey, because that's a very challenging and interesting experience. We built this camera, and this camera was to be flown in space, and space, as I told you, is a lot of vacuum, very limited atmosphere. And when we had to do this, camera had a high voltage system. And this high voltage system, as you know, that if you don't take care in operating it under various conditions, especially the atmospheric condition, it can arc. You would have seen this in rainy season, sometimes some of those transmission lines arcing. This is all because of the high voltage arcs with the atmosphere, and then it ionizes at that particular point, and you have a arcing system. Something like that was expected in this kind of so we had to test it. After testing it, when it was flown, even though we had tested it for 14 days, when we switched on the camera after 3 weeks, we found that there was a heavy arcing. The satellite was getting highly disturbed. We went into this. We had a standby system. We put that instrument into the standard system, standby system, and started finding out what exactly has gone wrong. And it was arcing, so we could operate the camera. And then we found that there was at a particular point, there were occluded gases. So the gas provided a path to arc, and therefore a high voltage system was connecting and it was giving. But engineers didn't give it up. They said that we should try to find we should get to the bottom of this problem. And then when they did more and more simulations, more and more modeling, they made also laboratory evaluation, like in space simulation chamber, which you see there. They came to the conclusion that there is a good possibility that this gas can come out, and then ultimately the camera can come out. The problem is, whereas if something goes wrong here, you can immediately fix it. When it is in space, you don't have any means of accessing it, except for a radio wave by which you can control it to some extent. So this was evaluated, and then we told the then chairman, Satish Dhawan, that there is a good chance that we should be able to recover. And he said that, okay, go ahead, I am not very confident that we are going to get this thing on order. But then finally what happened is, that after 6 months, the youngster predicted that will happen. We switched it on, and here was, lo and behold, the first images of this country coming from space. There was a setback. We tried to understand the setback. In the process of understanding the setback, we had this solution, and this solution helped us to recover back what was called as a failure of a mission, and we got the mission back. So this is a lesson that we learned, that these are kind of things on which best scientific talent, the best of the argument, the best of simulation, these kind of things are behind this. Today is becoming an order of the day. So this is an example of that right in the early phase of the space program. Similarly, we build another satellite. Primarily, this is for remote sensing, for using for communication and broadcasting, and that is called the Apple, an Ariane passenger payload experiment. Again, all satellite technology. But the interesting part of this is, whereas we can put this satellite about 500 kilometers, the Bhaskara, we need to put it at 36,000 kilometers, because at 36,000 kilometers, if you put a satellite, it has got a revolution period of 24 hours. The rotation period is 24 hours, so you find that that particular point remains stationary. So it becomes a tall tower, and when you have a tall tower like your television tower, which may be 50 or 100 meters, here is a tall tower of 36,000 kilometers, you can see one-third of the Earth. So you can see its potential as a tall tower for communication and television broadcasting. So that's the idea of building that particular satellite. We built that too. So we mastered satellite technology, we mastered the method of building a satellite along with a camera system for taking the imagery to the Earth. We built another satellite by which you can do communication. So all these, in the matter of something like 15-20 years, we mastered the entire art. Then we went into operational system. This was only study phase, evaluation phase, familiarization phase. From this we went to the operational system. Today we have INSAT systems. The INSAT systems today provide communication. It can provide broadcasting. It can provide meteorology. One of the interesting aspects of locating at 36,000 kilometers with a camera is you can look at the meteorological phenomena. Similarly, you can also have it for national satellite navigation, for position fixing. Then ultimately also we build the world's best satellites for remote sensing. I should say particularly for remote sensing. The remote sensing is also used for prying the adversaries. So this is not a technology that is easily accessible to many countries. So India was probably the third country to embark on a remote sensing satellite of the sophistication that we wanted, after United States and France. We had to build the camera system, we had to build the platform of the satellite has to be extremely stable if you have to take good pictures of the ground. And this satellite will be hoisted at something like 900 kilometers. And this camera should be sensitive enough to look at the vegetation and things of that kind. It is like taking a picture from Jaipur for a coconut plant which is located in Delhi. So you can see the type of power that the camera needs. So that is what was done for this kind of a thing. We again embarked on it with no information, right from first principles. We worked on, in a matter of 6 years, we built the satellite which was comparable to the contemporary satellite that the French and the Americans made. And this used camera systems, it used a variety of satellite technologies, and especially the stabilization system to look at the Earth. And some of the pictures that they returned were the most beautiful, and most importantly, we got to the point where Americans and French were there, right in the 1980s. And then somebody said that we can even go further, and then we built the world's best remote sensing satellites, which became a kind of a path-breaking system for the whole world to see. So in fact, it was again a challenge by some of the youngster engineers who said that if we can build satellites like what Americans and French have built, why can't we build satellites which Americans will say, why can't we build a satellite like what Indians have built? That is what he achieved in the next generation satellite system. This is the story of these particular 3 satellites, and I'm just giving you a type of a picture that is taken by the Indian satellite. This is a part of the UAE, they are developing those lamps. And you can see the beautiful picture that the IRS has returned from that location. It can take pictures all over the globe. So you have this kind of a thing. You can see a camera system from INSAT from 36,000 kilometers. This is a picture of the Philippine cyclone. Which was October 2000. You can see how well this can be tracked, and you can also see where exactly it will hit the coast. And these predictions now are available. We also have this kind of information, and also about the atmosphere, you can really predict where exactly a cyclone can hit the coast. This is another kind of an application. So just to summarize how our satellites are doing, you can see, you can use it, the remote sensing satellites can use it for agriculture, education, land, forest. Several of these resources today, timely information, accurate information, precise information in all these areas today are possible with the remote sensing satellites, and with the communication satellite we can use it. Broadcasting is about something like 200, about 1,600 channels today are provided by the INSAT system. You can see Doordarshan and many other television channels which are all coming out of the INSAT. You have also broadcast communication systems. It is also used for tele-education, something of interest. I am sure that the JNU is already using these kind of tele-education methods to connect with the best education centers all over the world. This is something that was used. We even promoted a satellite exclusively meant for education, the EduSat, coming out of the principles of communication, secure communication, rural communication. There are many things to which it is applied, and also using the synergy to look at a particular area which could be probably a disaster prone, and a synergy to look at communication we can also bring in as an effective tool for disaster management. This has been done for flooding, it can be looked for drought affected zone, it can also look at earthquake affected zone. So there is a whole host of things which can be done with this kind of a system. I come to the other interesting aspect. You know, when you go above the atmosphere, you have an unimpeded view of the universe. When you stand here on the Earth's surface with the blanketing effect of the atmosphere, it protects you, of course, in terms of ultraviolet radiation which can directly otherwise come. It also regulates the temperature of the Earth, otherwise the greenhouse effect and the climate change that we are talking for, this would have been not there if the atmosphere was not present. But then the atmosphere is really a protective mechanism for nurturing life on the Earth. But at the same time, it becomes an impediment for the entire electromagnetic spectrum to be seen from the ground. So you need to go up. So in order to take advantage of that, you build satellites to look at, say, how does the universe look like in the X-ray region? How does the universe look like in the infrared region? How does it look like in the radio region and millimeter region? So that is where the satellites are used for looking at astronomical observations of stars, galaxies, even multiple galaxies, and